Okay, hi everyone. So today we're happy to have Ronan Krause. Ronan is currently a postdoc researcher at Ludwig Maximilian University at Munich with Professor Monika Ivensberger. He got his PhD from Stanford, where he worked in a group of Professor Benjamin Lev. And that's what he's going to tell us about today. His interests lie in also cold atomic systems with a focus on quantum simulation of many-body physics. So thank you very much, Ronan.
Yes, I'm also happy to hear questions throughout, although I can sort of see when you raise your hand, so feel free to speak up. And I think my cursor should also be visible in case I need that.
Yep.
So yeah, I'll be talking about this work I did during my PhD, which I finished last year in a group of Ben Lev at Stanford, focusing on replica symmetry breaking and the observation thereof in an experimental system. And so before I really get to the meat of it, let me say a few things about spin glasses and what you need to know about these systems, as that's the context of this work. So we all know the paradigmatic Ising model, which is very simple to write down, and studied in much extent, but the interesting physics that I want to discuss happens when these pairwise interactions, JIJs, become disordered. And it turns out that many complex systems can be described by this simple quadratic binary Hamiltonian, if you will, which shows a lot of emergent behavior. And here are some examples where all of these systems can be described by this simple disordered Ising model. And why is this disordered Ising model so much more interesting than a ordered Ising model? Say, because if all the JIJs are positive, we know this system very well as a ferromagnet, and there's some interesting physics, but not that much. Well, the underlying reason is this competition between different spins. So if we think about just a triangle with these three spins with pairwise interactions, that two of these want to be ferromagnetic, but one is anti-ferromagnetic, then in this case, it's hard to describe or hard to find the ground state, and it depends on precisely the strengths of these interactions, because one of these spins is always frustrated. It cannot satisfy both of the bonds simultaneously. And this is, of course, just an example of a triangle, but if this happens in a large system, then frustration on a large scale leads to this structured energy landscape with lots of local minima in which the energy is kind of optimal, but not perfectly optimal. And finding the ground state of a spin glass system is equivalent to solving, for example, the traveling salesperson problem of finding the shortest route, which is to say that it is NP-hard. So that's a sort of computational description, but we do know at least some theory of spin glasses. And for that, I will focus on this archetypical model that's called the Sherrington-Kirkpatrick model, where the Hamiltonian is still the same, but I should now prescribe what these JIJs are. And so they are infinite range. All spins are going to interact with all other spins. And the JIJs are going to be drawn from a normal distribution with a parameterized mean and standard deviation scaled in the right way. And for this, you can actually draw up the phase diagram as function of temperature, and in this case, let's say the mean, which is shown here. Of course, at high temperature, the thermal fluctuations dominate. This is a paramagnet. And if the mean is strongly positive, then, as I said before, this is just a ferromagnet. And the interesting physics happens here in the spin glass phase at small mean and low temperature. And in physics, usually when we have different phases, we try to describe these with order parameters. And for example, the paramagnet to ferromagnet phase transition is described by spontaneous breaking of the all up versus all down symmetry. And this is captured by the magnetization order parameter, which is just here the definition. And it's zero in the paramagnetic phase and non-zero in the ferromagnetic phase, but the spin glass phase is also characterized by zero magnetization. For example, if we ask what precisely is the ground state, generically, this will be a pattern of spins pointing up and down sort of randomly. That depends precisely on the disorder interaction. And so to distinguish it from the other phases, we need a new order parameter, which is called the replica overlap. And that's this Q, and it has two indices, alpha and beta, for the replicas. And so what we intend to do here is sort of capture the fact that these spin glasses can break ergodicity and get stuck in local minima. So two systems with the same disorder interactions, or the disorder instance, which is usually called quenched, we freeze that out, can nonetheless navigate this energy landscape very differently and spend time in different local minima. And so if we compare these two systems at a certain time, they might or might not be in the same local minimum, and the overlap will be generically non-zero. And so that's true also for the ferromagnet. Of course, in the ferromagnet, you will find either of two states at very low temperature, being all up or all down. And the paramagnet is typified by zero overlap. So this is a little bit, the phase diagram here is just for illustration purposes, because this overlap parameter is really a distribution. So to illustrate that, I will show you some of these distributions. So for a ferromagnet in the ground state, you will find either, so that's to say at very low temperature, you will find either all spins up and all spins down, and the overlap, but if you find twice the same thing, so up or down, you'll calculate an overlap of +1. If you find opposites, you'll get -1. So you get these two sort of goalposts that correspond to finding the same state or same configuration plus its Ising symmetric partner. But for a spin glass instance, instead we can have get stuck in these local minima that might be entirely elsewhere in the configuration space. And so for one disorder instance, for example, there might be two good minima, one global minimum and one local minimum, where the overlap between these two is nearly zero. This is just an example. Here's another example. So if we want to think about this as an order parameter, we better not be sensitive to precise details in the disorder instance, and we can calculate a disorder average, which then looks like this. And this has been theoretically calculated that for an ensemble over this Sherrington-Kirkpatrick ensemble, the order parameter distribution looks exactly like this. So we still have the goalposts, because if you find a state once, you have some probability of finding it again, but also you have probability of finding sort of quasi-orthogonal states. I should say this structure is a bit surprising, because if you just draw random states, such as in the paramagnet, then you would find a Gaussian distribution that is centered around zero, because the configuration space is highly dimensional, so most of these are orthogonal. So that's sort of the surmise of Parisi that drew up the theory for this in the 70s and 80s, that the spin glass ensemble is characterized by a replica symmetry breaking. So the thing that the symmetry that is broken at the phase transition is replica symmetry. So two replicas behave differently, and they should behave in a way that follows this particular distribution or something like it for other models. But observing that in reality is actually quite tricky, because you need to have control over the disorder, be able to dial that in and repeatedly, and also you want to read out individual spin states. So you want to know what is the configuration, the full configuration of this system I'm studying. And so spin glasses have been studied in condensed matter context, where you have quench disorder in real materials, but getting a single spin resolution there is quite tricky. So in the rest of the talk, I'll tell you about the work we did to try and realize this in an experimental system in a different kind of context. So for that, I need to discuss light-mediated interactions in a confocal cavity. So that's the sort of context of ultra-cold atoms inside the optical resonator, which we can make behave as if they are an all-to-all interacting system. Then I will briefly discuss the spin glass model that we actually studied because it wasn't quite the Ising version, and then I will show you the experimental results. So as I mentioned, we put ultra-cold atoms inside an optical resonator. Here I'm illustrating a Bose-Einstein condensate. And we subject these atoms to a transverse pump. And once this pump is strong enough, the system undergoes a phase transition where the BEC develops a density wave, it orders in some way, and the cavity gets microscopically populated with light. And this is the context of this work. It's known under the name of a Dickey model. The main takeaway is to know that there is this phase transition. And above the phase transition, as I said, the BEC is ordered because the atoms want to form sort of a Bragg rating for the light to scatter into the cavity. So in real space, that means you have a checkerboard. And in momentum space, you have 4 Bragg peaks that correspond to it. And we can also detect the light that leaks out of the cavity, for example, on a photon counter, and see how, as function of time, this gets populated. So here, sort of the idea to have is that we start in what's called the normal phase without density order. We crank up this transverse pumping beam, and at some point we cross over into the superradiant phase. Now you might ask, well, why would the system do this? Because this density wave costs a bunch of kinetic energy to the BEC, and the compensating sort of term is the interaction energy. So light-mediated interaction between particles of the BEC inside the cavity gains enough energy to overcome this kinetic energy cost. So the picture is to have in mind is that you have an atom sitting inside the cavity, can emit a photon that bounces around until another atom picks it up, and thereby these two atoms are interacting. And what I also will say, which is important for understanding sort of the statistical physics later, is that this is a driven dissipative phase transition. So inherently, it is non-equilibrium. That means that we cannot make all parallels to the equilibrium physics of spin glasses, but I'll discuss this more later. So that's the platform, but it turns out you actually want to do a little more than just doing this in a single mode optical resonator. And so what the group of Benjamin, what we have pioneered is the use of multimode cavities. So you can pick special cavity geometries where the cavity field, the different modes, so here I'm illustrating the transverse electric field modes, some of these become degenerate. And then you can use many of these cavity modes and the physics gets modified. I mean, the story is still true that we have these atoms talking to each other, but now there's multiple pathways to talk through, like to mediate interactions. And that can then change the nature of these interactions. So in our experiment, actually, we have a tunable geometry that we can tune to the confocal cavity, the confocal resonance, or move it away from that to go back to the single mode physics. That's quite a convenient tool to have, but in this work, I'll focus on the confocal resonance. And having all these spatial electric field modes means that there is now also information hidden in the spatial degree of freedom of the electric field. So I showed you on the previous slide, the time dependence of the electric field that leaks out is worthwhile. Well, now we can also look at image the field that comes out. So not only can we take pictures by doing some kind of interference, we can do this holographic measurement that allows us not only to reconstruct the amplitude, but also the phase, and thereby the full intracavity electric field. This is a picture of the vacuum chamber with two mirrors. So it's a 1 centimeter long cavity with two highly polished and coated mirrors. And in between these two mirrors, we'll make BCs of rubidium-87. So I should say a little bit of math about what having all these modes does to the interactions. So this I'll offer you the math first, and then on the next slide I hope to give you a more physical, intuitive picture. But in the basics is just that, as I said, there's these photon-mediated interactions, and the interaction between atoms sitting at position x1 and x2 is proportional to the product of the electric fields summed over all the modes that are participating. And I should say that we have a body of works about this that Hai sort of works through the math, as we also sort of figured it out along the way. I don't think we fully understood everything as we started. But one of the important things to know about the confocal cavity is that actually it's not all the modes that are simultaneously degenerate, but rather it is split into two sort of families where parity is a good sort of conserved quantity. And so we can focus on a specific cavity resonance where all the even modes are resonant. And so we should remove all the odd modes from this sum, which of course I can just do by restricting the summation. And this is not the only thing to keep in mind. There's also the longitudinal character, so this is the transverse degree of freedom. But longitudinally, we know that these cavity modes, sort of the first few look like this, where you have one antinode, two antinodes, and three antinodes. And if we focus at the behavior near the cavity midplane, where we will put our atoms, this mode has an antinode at the midplane, but this has a node and this is an antinode. And so the longitudinal character of these modes alternates between cosine and sine. And so because cosine and sine are orthogonal, once the BC decides to organize into a cosine or commensurate with the cosine, it is not scattering into the sine. And so that means that sort of I can view these as two separate families, and my photon-mediated interaction is restricted to each family. In fact, I have one set of modes that looks longitudinally like cosines and another set of modes that longitudinally looks like sines. These are distinct parts of the interaction where R is now the transverse degree of freedom. Okay, now we can actually sum up these modes because they're Hermite Gaussians, and you can, through some math, get some expressions. And so these two sums are actually close to the same expression. There are three terms. The first is a local interaction. So when the two particles are near each other, there is a mirror interaction that arises due to this evenness of the cavity. And there is a non-local interaction that between the two sort of families has an opposite sign. So that's the math. But we can also think about this light-mediated interaction in a sort of physical picture that is maybe simpler, where we ask ourselves, if we have an atom sitting at position R1 that emits light, what kind of round-trip pattern would that light make? And so here's an illustration. As it gets reflected by the cavity mirrors, this light traces out a certain bow tie pattern that is specific to this confocal cavity. And one special property of the confocal cavity is that the length is equal to the radius of curvature, which means that for a curved mirror with radius r, the focal length is r/2, which is also exactly the distance between the mirror and the midplane. And so a point source in the center will emit a radial wave that gets collimated by the first mirror and then refocused by the second mirror. And so now we can see that the local interaction is just wherever there is light, there will be interaction is arising from being in the vicinity of the point source. The mirror, it corresponds to this focus across this cavity axis. And these two diagonal arms are, of course, this is a simple ray tracing picture, I should think about waves, they will interfere and form this cosine interaction. And so the confocal cavity is sort of a special imaging system where the midplane is both the object plane, the image plane, and the Fourier plane. And so another way to think about this is that this cosine is roughly the Fourier transform of these two terms. If I take c towards 0, these become delta functions, and the two delta functions give you a cosine. So we can then do an experiment that shows that this is really the light-mediated interaction, where we put a BEC at this radial position, drive this super-radiant phase transition, and collect the light that comes out, and reconstruct the electric field. And so here are some data on that. And we can see precisely the three features of this cavity light. We can see a bright spot where we put the atoms, that's corresponding to the local interaction. A mirror, so the cavity center is here in the middle, and then these stripes in the background are the non-local interactions. So this is an interesting system where we can sort of, in a way, learn from looking at the light that comes out of the system, also where the atoms were inside of the cavity and what they were doing. One thing I didn't specify is that by comparing the phase of the local field and the non-local field, we can learn something about the density wave phase of the, so whether it's cosine or sine. And so this system is kind of like a quantum gas microscope where we can really learn the microscopics, but in a way that also mediates the interactions by itself. And so for those who know a bit about optical resonators, the quantity of interest is the cooperativity. In this case, it's very high because it's enhanced by sort of this focusing of the light. In terms of the physics, we've previously done work with focusing on the local interaction, which is interesting because it can give rise to basically solids. You can create an optical lattice with sound waves, for which I refer you to this publication. But the non-local interaction is what we're interested in for studying spin glass physics, because one of the important criteria is that you can make the Jij sufficiently disordered. And specifically, it needs to be both positive and negative, and the cosine does exactly that. In fact, this cosine interaction is nicely controllable by choosing the positions of the BECs inside of the cavity can be tuned between a ferromagnet, a spin glass, and there's also another interesting phase in between. We could debate whether it's truly a phase, but it's a regime where the energy landscape is locally like a ferromagnet, but there is a few of those in the configuration space, and that can be interesting for associative memory purposes. So we'll use this non-local interaction to study spin glass physics. And of course, the other thing we need is an effective spin. We want to study spins. And again, there, the confocal cavity provides us what we need. Because as I mentioned before, there's this cosine kz and sine kz, the two different quadratures. But in principle, you can also make superpositions. And so the density wave phase of the BEC is a degree of freedom. In this case, I'm showing here that it sort of slides, and the phase is a U1 degree of freedom that can be identified with a vector spin. So if we put multiple BECs inside the cavity, each one is described by its own phase theta, and the total Hamiltonian that we get as mediated through these non-local interactions looks like this. I'm sort of skipping the math here, but you have pairwise interactions with Jij.
Can I ask a question? So
yeah.
I definitely, when you're saying you're putting multiple BECs in here, what do you actually mean by that?
So I guess this picture is maybe good. We put 8 BECs inside the cavity. So I mean, actually what we do is we start with 1 BEC and then split it into 8. The sort of phase coherence between the different BECs is irrelevant. I mean, all of this physics also happens for cold gases that aren't below the degeneracy point. of course, BCs have some nice features, but that's really the picture to have in mind, that we have sort of optical tweezers with which we control the positions of these 8 BCs, and we put them inside the cavity and subject them all together to the same transverse bond.
Thank you.
Yeah.
So are these coherently interacting, or are these just like classically interacting?
That's a good question. I guess I mean, as I said, the phase coherence between the two different BCs, so their U1 sort of order, the BC phase degree of freedom is irrelevant. So this phase coherence doesn't matter. There is coherence in the light field, right? So this light field has coherence, of course. Then we could say coherent light states, if the sort of amplitude is long enough, are exactly classical fields. And so we could debate about what exactly is the nature of this system. I think we know that the Dickey model at the phase transition is sort of seeded by the vacuum fluctuations of the cavity electric field. So there is some quantum degree of freedom. In the matter, the work I'm discussing right now is maybe more classical, because the BC is sort of a macroscopic object, but we also have proposals and some work describing sort of the spin half version of this system, which is sort of quantum in all regards. And of course, quantum spin glasses are a step beyond even classical spin glasses. The introduction was pretty much classical physics, and even that is poorly understood. So the physics we're seeing here with these BCs that are interacting and are described by a phase degree of freedom has an interesting form that maybe is more clear or sort of recognizable if I write it out in the components, where I take Sx to be cosine theta and Sy to be sine theta. We get this pairwise Hamiltonian with the JIJs, as I said, controlled by the non-local interaction that we can program via their positions. And then we have this XX minus YY term. So that's a bit funky, because I guess we're well familiar with XX plus YY. That's the XY Hamiltonian that has a U1 rotational degree of freedom. This is not quite that, and so it has different symmetries. In fact, it has a Z2 cross Z2 reflection symmetries. But other than that, it's a vector spin model. So because this is a vector spin model, also the order parameters are sort of upgraded. Of course, the magnetization is simply a vector, and the overlap we can calculate component-wise. It's a 2 tensor. It's a matrix where we can look at XX and YY overlaps. I'll ignore the off-diagonal overlaps. These don't seem to play a role, and I'll focus specifically on these two quantities, the sum and the difference, capital Q and capital R. And as far as we knew, this model hasn't been studied in the literature, so we can ask first, what are the equilibrium properties via doing standard technologies such as parallel tempering Monte Carlo, where we can aggregate many disorder instances, thermalize them to a certain temperature, and get distributions. So the top panel here shows the magnetization distribution, which is centered around 0 with some spread set by temperature and finite size effects. And here I'm showing you the overlap distribution as a 2D diagram with Q and R. And I specifically chose Q and R because if you sort of project this, I think maybe I don't have the animation here on this slide, but if I look at the projection on the Q axis, then I have sort of two goalposts here, these two edges, with a smooth continuum that is filling in between. And so indeed, this vector spin model hosts a paramagnetic phase at high temperature. It hosts two kinds of ferromagnetic phases, because kind of the X direction and the Y direction can be ferromagnetic separately. and then there is a spin glass phase. And so the sort of phase diagram here, or the looks roughly like this. Okay, these are the order parameters as function of temperature, and again the mean J, where now negative mean also is meaningful to study, which results in this Y ferromagnetic phase. So if we compare and contrast these order parameters, the phase diagram roughly looks like this. So high temperature paramagnetism, low temperature spin glass, as long as the mean of the interactions is roughly 0 and bordered by 2 kinds of ferromagnetic flavor. And yes, this is the thing I wanted to show you earlier, that if we project on the Q direction, this is really sort of it's a generalization of the Parisi distribution for vector spin models.
And should I have any worry about that this is 8 spins?
Sorry?
Should I be worried that we're talking about 8 spins here and you're drawing phase diagrams?
Yes, so I mean, what I'm showing you here is parallel tempering Monte Carlo for, I think we did it up to 128 spins.
Okay.
Indeed, the experiment will be limited to 8 spins. We did some finite scaling studies that show that one of the things that I think is important here is that it's vector spins. So if you have 8 Ising spins, the configuration space is kind of small because it's just 2 to the 8. But here it's vector spins, and so there is already kind of a lot of degrees of freedom. We thought that this actually helps sort of makes you converge faster in terms of finite size effects, but it's a valid concern, I guess. I mean, you know, when you do something for the first time, you always have to start reasonable, I would say.
Should I also worry about whether Jij are genuine, like independent random numbers compared to here, right? Because Jij follows a deterministic expression.
Yeah, so that's also a good question. I think that can also be, so we theoretically studied this Jij construction, and as it turns out, we can just, like, you can do random matrix theory and look at the spectrum and the eigenvalue splitting. And so there is this relevant length scale, right? The expression
W naught.
Yeah, there is a W naught that's related to the cavity physics. It's the cavity waste. And so if you sprinkle all your atoms or BCs sort of within a radius that is this waste, then of course, well, that's exactly where this interaction gives you a ferromagnet, because cosine of small numbers is just 1. But if you go far enough out, then this cosine and it's Ri dot Rj, and so it sort of goes like cosine R squared, it becomes sort of scrambled fast enough that you just get a semicircle distribution and the Wigner surmise. Again, you could say for 8 spins, maybe you have to be a little bit careful, but we analyzed the disorder instances we studied, and they look roughly like a semicircle with maybe a little bit over representation of sort of 0 eigenvalues. I think it's, in the end, doesn't matter too much. I think in principle, as long as you can average over the disorder, this is pretty forgiving. But it's good questions. Yeah.
So how do you average over disorder, right? Because do you average over W naught, or do you?
No, we just put in different positions. So actually, I'll get there. But first, I want to demonstrate that we have sort of precise control over the positions. We first wanted to make one of these ferromagnetic phases. And so I can put 8 BCs inside the cavity, drive them across the superradiant phase transition, and look at the light that comes out. And here I'm showing you just a standard imaging, so not holographic. You will see 16 spots. That's again because of the mirror symmetry. So the cavity center is here indicated by this cross. And from the positions, these radial positions, I can then stick these into the Jij calculator and get a matrix out. Now you might say, wait, that's not a ferromagnet, because you just told me for a ferromagnet, the mean of the J has to be either strongly positive or strongly negative. And that's because this is sort of a hidden ferromagnet. It's a ferromagnet for which 4 of the spins are sort of flipped. So if I perform a local gauge transformation on those 4 spins, I do recover a J matrix that is all positive. Okay, there are two elements that are slightly negative, but it's still a ferromagnetic energy landscape. You know you can tolerate a few anti-ferromagnetic interactions that don't ruin your ferromagnetic order. And so we're just looking at this ferromagnet in a wonky way. The technical term is a one-component Mattis model. And the important thing to remember is that we need this local gauge rotation to make it more obviously ferromagnetic.
So it just means that your disordered distribution is always frustration-free.
Well, for these particular positions, it is frustration-free, yes. There are other positions that we can dial in, and we will do later, for which it is frustrated.
Okay.
But in this case, we wanted to do the ferromagnet that does not have frustration. So from these positions, we get the interaction, and then we want to know how did these spins organize themselves, and for that we switch to the holographic imaging, where we now get this colorful picture. Here I show you our way of displaying this. So phase is represented in color and intensity with brightness. And if I sort of zoom in on the relevant bit, we can, as I said, the phase of the light conveys the information of the phase of the density wave, which was our spin degree of freedom. And so through some image processing, we can then extract the spin state, which I show here as these arrows. And so you have to remember that there was this, I needed to flip 4 of the spins. Of course, I already knew which ones to flip, and if I flip those, it's exactly the ones that were orange. In this case, all of the spins are sort of co-aligned along the x-axis. This is exactly the X ferromagnet that I intended to make. And so this is a single experiment. We can, and as you can see, not all the spins are pointed precisely along the X direction. There are some deviations. Part of that is finite size effects, but part of it is also, and finite size, I should say, finite size of the cloud. Like each BC has some finite extent, and this muddies the waters a little bit. Because the left side of the cloud and the right side of the cloud are in principle, they're mostly rigid, but a little bit can be flexible, sort of. And we know how to sort of coarse grain that away, but it results in some deviation from the pure X degree of freedom. But of course, there's also some effective temperature that allows you to sort of rotate around the ground state. And so we can repeat this experiment. This was, I think, close to 1,000 times, and build up the histogram and see that the magnetization, which is the right order parameter here, is either +1 along X or -1, which is exactly what we expect for the ferromagnet. And we also can show that this is spontaneously broken at the phase transition. We can also calculate the overlap, and in this case, we get sort of these two opposite corners. Of course, Ising symmetry still says that it always has to be reflection symmetric. So the better way to say is we got one corner here. This is the equivalent of the ferromagnetic goalposts for this vector spin system. And from the ensemble of states, we can, because we know our Hamiltonian, we can simply calculate the energy of each spin configuration we saw, make a histogram compared to the ground state energy, and this red line is a theory curve fit for an effective temperature that is based on the local density of states, and captures the experiment pretty well, and shows that we are well in the ordered phase. Of course, I mean, we knew that anyway from looking at the order parameters, but it's a relatively low temperature. So that's the one flavor of ferromagnetism. We can also get the other flavor if we move the position slightly. So here we program in different positions, repeat the same kind of experiments, and now we see that actually the spins are all pointing down or up. This small tilt is we understand. And again, it has because it's the Y ferromagnet, it now occupies the opposite corners. And it is still roughly described by this Maxwell-Boltzmann distribution with a low temperature. So that's to say that we have precise control over configuration of, or this precise control over the position of the spins and thereby the disorder instance. So now we want to do the interesting glassy physics. So we move the atoms again to yet another position where now this is a frustrated J matrix. And we keep it there and rinse and repeat the experiment. Well, on the first try, you see some kind of pattern come out that has no obvious order, exactly as you expect. And then as you rinse and repeat the experiment, you see other configurations come out. These are the sort of 4 most common. We repeated this 100 times. Configuration A, which corresponded to sort of the lowest energy configuration, was found 50% of the time. And then if I remember correctly, it was something like 20, 11, and 9% for these other configurations. So this is exactly what you would expect for these spin glassy systems, which is that sometimes you catch the system in a local minimum. And so that's exactly these other configurations. So taking the 100 ensemble or the 100 sort of repetitions of the same experiment, and we know that this is the same disorder instance because we can control the positions well enough for that. We can then take this aggregate and make the disorder or the order parameter, the overlap distribution, where we can identify multiple interior peaks that correspond to different spin configurations you find. Of course, if you find the same configuration twice, you will be on these left and right edges. That's what I said earlier about this sort of goalposts for the that the ferromagnet has and that the spin glass also has for finding the same configuration multiple times. But we also see these interior peaks. In this case, it's sort of 2 prominent peaks with maybe a third that is a bit weaker. So that's precisely what you expect for an individual disorder instance. And one of the things that we can do is by sort of changing the speed at which we ramp this system through the phase transition, control sort of the amount of, or in some semblance of effective temperature. And now it gets complicated because the parallels are not precisely as I said before, it's a non-equilibrium system, so I don't want to give the impression that everything is described by a thermal equilibrium statistical mechanical ensemble. But qualitatively, we see this picture that if we ramp faster, these peaks wash out because you can tolerate some sort of spin flips or spin deviations. Whereas if you ramp slower, if you ramp slow enough, you mostly find the low energy configuration all the time. And of course, that you can understand as being an 8-spin system. There is a finite gap between the ground state and the first sort of local minimum. And if you go slow enough, such that in some sense you can resolve this, you will find only the ground state. So that's this idea of having sort of lower effective temperature with the caveat that it's not thermal equilibrium. But yeah.
Sorry, yeah, so can one say anything purely based on the experimental result that this is not some sort of critical slowing down, but it's really just glassy physics? Like if I don't have any numerics to compare to.
I'm not sure. I guess, well, we do have the numerics to compare to it, but also, I guess it's a question of if it has all the right order parameters, is it the phase of matter described by those things? And I would say probably yes, although I'm happy to hear counter examples.
Yeah, I guess if I want to just check the experimental result, hopefully self-consistently, then the smaller amount of numerical input, the better. The numerical stuff relies on having confidence in the model.
Mm-hmm.
May has its own issue. Well, I don't know if the system will enough, but just sort of a general call.
Yeah, I guess I'm not precisely sure. I think I'm also not sure what the sort of standard is for condensed matter physicists who take a sample that has frustrated interactions that they then put under a microscope and claim it is a spin glass. I guess I'm not exactly sure what the observables are there either. I mean, there, of course, you can do, the typical thing, I guess, is this susceptibility peak and the difference between zero field cooled and what was the other term? Like there is hysteresis in how the system behaves as you cool it down with a magnetic field or without. And of course, these are the kind of experiments that we are thinking about now also, where you can use an external magnetic field and try to look at how the susceptibility diverges at a certain point. Maybe those are more traditional methods for demonstrating something to be a spin glass. I'm not sure. I guess you have to do the whole suite of experiments, no?
Thank you.
But what I would say, I guess, is if we are talking about replica symmetry breaking, is that this is sort of the purest way in which you can observe replica symmetry breaking, which is that two copies of the system that you have to prove that they are precise enough copies, and so we do have some position disorder, but that this doesn't completely corrupt the interaction matrix. That two copies behave differently is an example of replica symmetry breaking. Of course, there's always the discussion of a finite size system where you can never see true symmetry breaking unless you have an infinite size system. And so it's a divergence of timescales at which the system flips to the other symmetry state, sort of. But so this is exactly what you would expect for a system with a single disorder instance. And so then what we did was repeat this procedure for multiple disorder instances. And so we program in a new position, repeat the experiment 100 times to get the different spin configurations and calculate overlap distributions. And here are some examples. And then we did do some numerics to match sort of, or qualitatively compare these overlap distributions. So the equilibrium simulations, so the input to all of these is the interaction matrix that we believe we made. We can also measure in some sort of circuitous way. And then perform parallel tempering. Well, it shows replica symmetry breaking, but it doesn't precisely match the observed spin overlaps in the sense that there is no temperature at which it looks exactly right. And I think this is related to what I said earlier about it's not an equilibrium system. So if instead we do some trajectory simulations of the mean field equations of motions as we cross this phase transition, then we get qualitative results that look quite like the overlap distribution. So this bottom row is the result of that. And some of them, it looks better than others. I think this last one, for example, seems quite sort of obviously different. And we don't fully understand why that is. Part of it could be that the interaction matrix is slightly different than what we believed we put in. Of course, in general, this is quite tricky because I think in a spin glass, as the system becomes larger and larger and more frustrated, you become more sensitive to small changes in the J matrix. Of course, those can sort of shift the energy, the local minima up and down by enough that they are disfavored, for example.
So Ronan, I think it's clear in my head how this putative spin glass is different than the ferromagnet, right? Do you have some picture or storylines on how it's different than the paramagnet?
I think the reason why it's different from the paramagnet is because we see these configurations many times. So I think for a paramagnet, if you're at high temperature, you expect it to be like just a random number generator, basically, a random spin configuration generator. But we see that the same configuration is found at like 50% of the time or stuff like this. The corresponding thing for the overlap distribution is that for a paramagnet, you would expect to see a Gaussian centered at the center here with some width that is set by temperature and finite size. So the fact that we still see stuff on the edges is just a sort of translation of the statement of before, which is that you find the same state multiple times.
Right, and if you have 8 spins, though, the number of states is fairly small. So
yeah, I mean it's u1 to the 8. Right? It's a vector space, so it's actually not that small.
Yeah.
But it is small, and of course there's not a sharp phase transition between the paramagnet and the spin glass phase. It's a rendered a crossover. And now I have to remember whether we put specific cuts of the parallel tempering results there. I don't remember, but you can see, I mean, you can, along this cut, you could study the overlap distribution and see a transition from a Gaussian into sort of the Parisi distribution. Yeah, so I think one of the things that would be nice for us for the experiment is to also sort of map out this crossover, try to get a handle on the temperature and dial it in across sort of this phase transition. This was, well, even this experiment was I think 3 months of data taking, because each disorder instance you requires 100 shots, and then we wanted to do 120, like enough disorder instances that we had some confidence in the disorder average. Of course, I think there are interesting physics questions about what does this crossover look like exactly. Yeah. So yeah, so as I mentioned, we wanted to do a disorder average. So this is 4 of them. Then we just kept going until we aggregated a reasonable number, where reasonable was studied with numerics to see how long it takes to converge, sort of. And so we see this kind of aggregate overlap distribution. So of course, the important thing is that you sum the overlap distributions, but not not put all the individual configurations on one pile. And again, we can do some kind of numerical simulations. This is actually a little bit trickier than these ones, because we didn't want to measure the Jij matrix for each of these. And what I show you here is now sort of the Parisi order parameter, and it has some interesting features that I'll comment on. And I'll show you also again the 1D projection, the marginal. But I should also show you the magnetization, because it's kind of meaningless to show one but not the other. And so this is the magnetization distribution that indeed shows it's Z0 with some spread set by temperature and finite size. And this white-blue scale is kind of hard to really make a clear statement about the continuity here of the distribution. This becomes clearer if I show you the marginal. And so here we can see, this is on the Q-axis, the 2 goalposts that you get always, and then a sort of continuum-looking thing in between that it quite clearly isn't as continuous as one would expect maybe from a Parisi distribution. And what I've drawn here on top is actually these dashed lines are 9 equally spaced dashed lines, which line up quite well, at least with some of them, or some of the peaks are not so prominent, but it does seem that each line has a peak under it. And these positions are exactly what you would expect if you had a Ising spin system, because for an Ising spin system, there's only, or we have 8 particles, then there's only 8 plus 1 possible overlap values. And so what we think is going on is that there's some weak binarization happening in this system. It's not along a clear X or Y axis, otherwise we would have seen that in the magnetization, but rather there is some sort of easy axis that is also random, and we have some ideas sort of about how that could be the case in the experiment. But also there is still continuous support. I think this is on a logarithmic scale, but nonetheless more than 10 to the 3 counts in each bin. And so that shows that there is this Parisi distribution that you get for this system. And so, as I said, the next steps are sort of understanding precisely what does the non-equilibrium effects do to the system and make it different from a simple thermal equilibrium statistical mechanical model. There are some of the measurements that are interesting to perform to sort of connect with what traditional spin glasses are characterized, such as susceptibility measurements. Although now that we have this sort of system where we can resolve individual spins, we can also perform these susceptibility measurements on individual spins. So we can make a local magnetic field. Of course, everything is done by light, so we just focus the light on an individual BEC and ask it how susceptible it is to this magnetic field. And one of the other avenues of interest is sort of going to this intermediate regime where there are certain local minima that mean something to you, the spin configuration that you want to restore such to have as a memory. And then maybe a bit more of an outlook is that what I showed you here is this vector spin glass, which is maybe not the cleanest way of studying what is known in the spin glass literature. So for that, we would want to go back to Ising spin glasses, and we have done some work by where the cavity physics is actually a pseudo spin half system by using 2 internal states of the atoms. And so that's one avenue to explore. Another interesting idea is what I showed you here is infinite range interactions, where people more or less believe that these systems are spin glasses. But short range interacting spin glasses are a different story, where these are much more hotly debated about whether there is replica symmetry breaking, and if so, in what dimensions. And it's typically believed that somewhere between 3 and 6 is the dimensions is where the cutoff lies. And using our local interaction could be an interesting avenue to sort of perform simulation of these systems. And lastly, I mentioned quantum spin glasses. If we make each individual spin degree of freedom a quantum spin, so truly spin half with the right commutation relations, then this also becomes a very interesting avenue. And here I mentioned before, we have done some theoretical work that studies the quantum dynamics. So far above threshold, this was easier to do first. We actually looked at the effective dynamics, and it turns out that the cavity, the dissipation naturally realizes steepest descent dynamics. And near the phase transition, we have a recent PRX that studies the role of entanglement near this phase transition. So with that, this is the team. So that's Benjamin, the collaborators, and the rest of the team that was before I finished and left, and some funding agencies. And then I'm happy to answer any more questions.
Thank you very much. Further questions for the speaker? Quite a few.
So I'm going to ask another one. So Ronan, if you did want to make an Ising order parameter instead, could you just put a longitudinal optical lattice that's at half the period of the? Yes,
that's exactly one of the 2 ways. So actually, right before we did this work, we really wanted to do Ising spin glasses. So I think I spent a year or 2 trying to do exactly that. So combining the internal degree of freedom physics with an external lattice that pins the motional degree of freedom. That turned out to be not super fruitful. And I think maybe you were also suggesting something slightly different, which is, if I may rephrase, the confocal cavity is nice, but it has this, because it can mediate interactions through all of these modes, but it's kind of too multi-mode for what you want to have if you want to do Ising physics, because it has cos kz and sine kz longitudinal modes. If you somehow can get rid of half of these and only keep the cos kz, then that is an Ising degree of freedom, because it can do either plus cos kz or minus cos kz. That's exactly a sort of pi Z2 spin. And so the confocal cavity does not lend itself to that supernaturally. And you could try to make it work with a optical lattice. I think in my thesis, I put some work on this. But there are sort of other cavities that are more promising in that regards. So that is, I think, something they are thinking about or currently working on in the lab at Stanford.
Other questions?
Yeah, I have one. So just right now, you mentioned that with this super radiant phase transition, you have some interesting entanglement behavior near the critical point. Actually, could you elaborate a little further on that?
Yeah, sorry, what was the last?
Yeah, so you said there's interesting behavior in the entanglement near the critical point.
Yeah, so what we studied is that if you start, this was done in an Ising spin system where you have the quantum spins and then otherwise the same effect. So you have non-local interactions and you take this system through the super radiant phase transition. And we unraveled the master equation into trajectories and numerically simulated this. And of course, then you can keep track of everything that happens. Well, in the spin sector, you have to trace out the cavity light, because this would otherwise become too unwieldy. But you can keep track of the entanglement and calculate things like this. And so it turns out if you it's precisely entanglement. I'm showing you here also a sort of representation of this trajectory. So the idea is that you start on the South Pole, which is the ground states. All the spins are pointing. Okay, this gets a little bit complicated, but the spins are pointing sort of out of the Ising direction. And at the end, they want to have an Ising interaction along X. It's SX, SX. And so the spins go into the interior of the sphere, which can only happen if you're entangled, and pop out to the side. And what this means is that this entanglement allows you to find sort of low energy configurations, because there's a classical barrier that arises near this phase transition between sort of the two different bases, the normal phase in which all the spins are pointing down, and the superradiant phase in which the spins want to point either in plus or minus X according to the ground state of the frustrated interaction. And so, of course, there are some you can, if you go adiabatically, then you can avoid this classical barrier, or you just stay right on top what is allowed, but the entanglement allows you to go through. And do I remember another punchline? I think that was the main punchline. And then we looked at how this system then breaks the replica symmetry, because you can do this again and repeat trajectories, make overlap distributions. And there we also saw it's not captured by a thermal ensemble of spin half particles. It's already starting to show some effects from the non-equilibriumness of the system. But I encourage you to read the manuscript if you are interested in more of the details.
Thank you.
Yeah.
All right. If there are no further questions, let's thank Ronnie again. Thank you very much.